So I want to talk about another ionophore. I'm going to talk about valinomycin. Okay, so just if you hadn't watched this video prior on 2,4-dinitrophenol where I introduced the concepts of ionophores, just want to sort of mention it here. So ionophores are compounds that move ions. They are passive mediated transporters, meaning that they dissipate concentration gradients. Energetically, they are downhill. They're going to have a negative delta G, and that's because they move substances from areas of high concentration to areas of low concentration. They're mediated because they need some type of a gate, a transporter. Oftentimes they're proteins, but with 2,4-dinitrophenol and valinomycin, these are not specifically proteins. They're substances that are going to allow us to pick up an ionic species from a high concentration side. And because of a change in their chemical properties, if we're talking about 2,4-dinitrophenol, that was a protonation state, or in the case of valinomycin, it's actually what the chemical structure is. It's allowed to flow through the lipid bilayer and then deposit that ion on the other side, dissipating the proton gradient. So we're going to understand how valinomycin works by looking at its structure. So I first want to highlight what valinomycin is. It is an antibiotic. How it works is it's going to dissipate a potassium gradient in bacteria. Okay, so that's how it works to do its antibiotic sort of chemistry, but we're going to look at the structure of it specifically to understand how it works. So I want to highlight that this drug, I've got the structure of the drug here, but this is a little bit hard to see in terms of exactly what it is, but it is a macrocyclic compound. Said in another way, it's really a ring structure. So when we think about this, what we really have is we are going to have this backbone. Let me actually do this in green here. It's going to make more sense in a minute why. But we have a cyclic structure. Here's the backbone, and then we repeat it 3 times so that we have these all connected. Okay, so we're going to have this macrocyclic ring structure. So you can sort of think of it like being a charm bracelet. We've talked about that with protein structure. And what we have dangling off is going to have a lot of impact here in terms of how this structure performs its function. So I want to zoom in here and have us think about this. This will be a good opportunity to review some things that we've already talked about. We can see there's essentially going to be 12 different pieces that are sort of connected here. Okay, we've got them color coded here. We've got sort of 4 substances that are connected together in this order, and then 3 of those 4 residue repeats are connected together. So sort of 12 pieces total. I want to highlight and draw attention to some things that we've already sort of talked about. Here we have the amino acid valine. We see it in the L and the D flavor. So the only thing that is quote unquote natural about this structure, or sort of found naturally, is this guy. So I want to sort of highlight here. This is a naturally occurring amino acid. And when I say naturally, I mean what's found in you. Important thing to remember is we've got amino acids that are L in their stereochemistry, sugars that are D. Okay, so this is actually more of a non-natural amino acid, but we can see that we've got our NC-alpha carbonyl, so it is an amino acid, our same NC-alpha carbonyl that we have here. So when we connect things together, we are going to be making linkages. Well, look at this guy, okay? Notice these 2 amino acids aren't hooked together, so we're not forming a peptide bond between these guys. But what we're going to have here is we're going to have hydroxy isovaleric acid. So what we're going to have here, this was a carboxylic acid functional group. This was an alcohol. So we can do chemistry between these functional groups. We've got carboxylic acid plus an alcohol gives us an ester. We've got carboxylic acid plus an amine. That's going to give us an amide. So notice what these linkages are. I would expect you guys to be able to look at all of these and make sense as to why. So this is an ester linkage. Here is an amide linkage. And let's look at our last linkage that we sort of have here. We've got lactic acid. Okay, so we've got lactic acid here. We're going to have another alcohol group. This was a carboxylic acid. If you look up the structure of lactic acid here, we're going to have another ester linkage. because we combined the carboxylic acid from that valine residue with the alcohol from our lactic acid, and then coming back around here and connecting our final linkage here. Remember, this is going to be a carboxylic acid from lactic acid hooked to the amine group from that valine residue, and so we have our last sort of amide linkage there. So ester amide. But that's not really the part that's important here. Okay, I want to highlight that if we think about sort of what the charm bracelet part of this is, what are the things that dangle off, particularly as we have two amino acids. The amino acids being valine are going to have nonpolar side chains. This dihydroxy isovaleric acid, basically it has a valine-like side chain that's there. And then lactic acid, we can think about it having a side chain as a methyl group. So we have a lot of non-polar pieces here. All right, so now that we've looked at and picked apart this structure, I want to map it on to what we actually see here with the structure. So I want to map on the things that we sort of see here. So everything that we have in green, we can sort of think about as our backbone here. And this doesn't show up super well, but here's our backbone for all of those pieces. That's sort of our charm bracelet, okay? And hopefully what you sort of see here, here are all of these sort of isopropyl groups. That's sort of what those are, okay? We can see all of these isopropyl groups sort of dangling on the outside here, isopropyl groups, methyl groups from time to time, right? But what we have all on the outside here is greasy portions. So these are greasy portions. And I want to highlight what the inside of this looks like. Okay, so I'm going to sort of highlight in a pink color so we can see it pretty well. I want us to take note of this carbonyl that we're going to be seeing. We've got this carbonyl repeat, whether it's part of an amide or an ester linkage. Okay, that's what we have here. All of these carbonyls that are part of either esters or amides, they're all pointing in the middle, okay? And those are going to be very hydrophilic. So again, I'm going to highlight these in blue here, okay? Not necessarily going to show up, but that's why I also have the pink, okay? But these are very hydrophilic. Okay, so what this means is we've got greasy on the outside, but hydrophilic on the inside. So what I want you to think about with this structure is a reverse micelle. Remember when we talked about micelles? Micelles were formed when we had fatty acids with a hydrophobic tail and a hydrophilic head group all associated with one another. These greasy tails, and we talked about, I want you to think about like a drumstick ice cream cone, right? All of those greasy tails want to find one another, so they're going to form the center of our micelle, and all the hydrophilic ice cream cone head groups are all going to be on the outside. That's how we typically think of with a micelle. This is the opposite. This is like having all of the ice cream cone parts or the ice cream in the middle and the cones pointing out, okay? So that's what this molecule is going to look like on a structural level, is a reverse micelle. So you might say, well, why is that important? And what's that big purple thing in the middle? Well, this big purple thing in the middle is a potassium ion. So what happens here, and let's sort of go back to this picture to show, this is our reverse micelle. What it can do is it can grab a potassium ion that in no way would transit the lipid bilayer by itself, but it can bury it on the hydrophilic inside of this drug molecule. And then because it is greasy on the outside, it can easily transit to the other side of the lipid bilayer and literally spit out that potassium ion on the other side. So it dissipates potassium gradients in bacteria. If you discharge important ion gradients, that is going to be lethal. So again, the discharge of an ion gradient is what makes this be lethal in, or I should say to, bacteria. Right? So that's the antibiotic valinomycin, another example of a carrier ionophore.